Alright, welcome back. Math1720, Chapter 8, Section 2. We're going to hop right in here to polar complex numbers, or polar form. Okay, we'll go over what those are. So last time we briefly touched on, what a complex number was. We had a real and imaginary part. Now we're going to be able to go back and forth between rectangular coordinates, which is in terms of x and y, into polar coordinates, where we have a magnitude and an angle as such. Okay, so when we start approaching these and graphing these, we know that the horizontal axis on the Cartesian system is what we call the real axis, and the vertical axis is going to be the imaginary axis. So when we graph things in the complex plane, x is real, y is imaginary. So that's how we're going to graph our complex numbers here. So if we take a look at this example here, all right, we have 2 minus 3i. So we go 2 to the right, that's in the real axis, and minus 3 in the imaginary axis, so we go down 3. So our complex number would look like this vector that's shown here on the example. 2 minus 3i would get graphed into the fourth quadrant. So just keeping in mind, horizontal axis is the real axis, vertical axis is the imaginary axis. So, just the sum of two complex vectors is still the resultant vector, so none of the rules of vectors that we learned in Chapter 7 are any different here. Alright, we just have to keep reals with reals and imaginaries with imaginaries. So if we have this example here for this resultant vector, we have 4 plus I plus 1 plus 3i is equal to 5 plus 4i. So on the left-hand side, we're able to add the 4 plus 1, that's the real part, and get 5 for the resultant, for the real part, and we have I plus 3i gives us 4i for the imaginary part. Okay, and then we're still able to graph this. So we go over 5 in the real axis on the right, the horizontal axis, okay, and we go up 4 in the imaginary axis. So pretty basic there from what we've done. Alright, so let's just do another example here. We want to find the sum of 6 minus 2i and negative 4 minus 3i and graph both the complex numbers and their resultant. Okay, so the first one, we're going to go 6 right, 2 down. The second one, we're going to go left 4, down 3 when we graph that. The resultant vector, right, should be 6 plus negative 4. So we're going to get 2. We have negative 2i minus 3i, so we're going to get negative 5i. So that should be our resultant vector when we do this. Okay, so very simple, reals with reals, imaginaries with imaginaries. And when we graph these vectors, we graph them from the origin, okay, and then we graph, remember you're graphing it as a vector, so it has a head and a tail, or an initial side and a terminal side. And just like before, the resultant vector, we're going to lie in between those, okay, and make your parallelogram if you need to. Okay, let's talk about the relationship between rectangular coordinates and polar coordinates. So obviously rectangular coordinates are in terms of x and y, and polar coordinates are going to be a magnitude and a direction. So x and y, okay, those are the rectangular coordinates too. So to find x, we're going to take r cosine of theta, where r is the magnitude of the vector, and then to find y, we're going to take r sine of theta. If we want to calculate r, we're going to take the horizontal component and the vertical component, or the horizontal piece and the imaginary piece. Alright, and we're going to apply the Pythagorean theorem. So it's going to be x squared plus y squared all square rooted. So that's r. And then in order for us to find the direction of the vector, we will always take tangent inverse of the vertical over the horizontal, or the imaginary over the real piece when we do this. Okay, so a lot of everything that you're going to be doing in this section is around these 4 equations right here. Okay, so another kind of just different form of what we're doing here. If we take the trigonometric form, it's technically the polar form. We can rewrite this instead of saying x plus y, because x is r cosine theta and y equals I sine theta. We can write it as r times cosine of theta plus I sine theta, and we write it in short. Okay, so this CIS, cosine imaginary sine theta. So if you see CIS on a few of your homework assignments, that's really all it's asking you to do is take r times cosine of theta plus r times I sine of theta. Okay? So just a shorthand notation. So when you see RCIS, it really means r times the quantity of cosine of theta plus I sine theta when you're doing the calculations. Okay? Now, R is called the absolute value, the magnitude, or when we're talking about complex numbers, we call it the modulus. The modulus, that's just a special name that we have that's applied to the complex numbers instead of using the word magnitude all the time. The modulus is tied so that we know that the number is purely, well, it has a real component and an imaginary component, whereas magnitude is always just purely real. Okay? Theta is what we call the argument of x plus yi. Okay, so what we're going to do, let's do an example here. We want to take, this is in polar form. Okay, we can tell by the way it's written, and we want to express it in rectangular form. So remember, to find rectangular form, we're looking for x and y, and x equals r cosine theta, and y equals ri sine theta. Theta in this case is 300, so we're just going to substitute in. Make sure your calculator's in degrees mode when you do this. Okay. Now we're going to do it this way, so we know our cosine of 300 is equal to 1/2. Okay, you can use your calculator and get values too, but this is if you didn't have your calculator, because I know some of you are still missing yours. But we can calculate those angles as well, right? Using a reference angle of 60. So sine of 300 is negative square root of 3 over 2. So we substitute in those values. So cosine of theta is the 1/2, and sine of, I'm sorry, I can't talk right now. We have r is 2, all right, and then we have cosine of 300 is equal to 1/2 minus sine of I 300, which is square root of 3 over 2. So we can simplify this down into its rectangular form, and then since we have a 2 on the outside of the parentheses, we're able to distribute it through and simplify, so the 2 in the numerator cancels out with both of the 2's in the denominator if we were to factor out a 2 in the denominator. And our final answer is 1 minus I square roots of 3. Okay, you could have done it in your calculator as well. The reason the calculator piece might be a little harder is because it's going to always give you something in decimal if they don't work out nicely. And you got to be able to kind of take that decimal and make it into a fraction. But on your homework, it's more or less turn all the fractions into a decimal and compare with what you got sort of scenario. Okay? Alright, so if we want to convert from rectangular to trig, it's always a really good idea to sketch the graph so we can see the real and imaginary in the complex plane, and then find r, the magnitude of the modulus, right, by taking x squared plus y squared and square rooting it. And then we find theta by taking tangent inverse of y over x. I know it doesn't say tangent inverse on the slide, but tangent inverse of y over x is the actual theta that we're looking for because that's the direction. Alright, also make sure that you're always in the right quadrant when you're sketching. Okay, so let's take this expression here. It's obviously complex, right? So we're going to take negative square root of 3 plus I. And we're going to write that into trigonometric form. Okay? So when we can graph it, alright, and then just kind of know what our triangle is. Okay, so if we sketch that graph, it's going to look similar to this. Alright, what's the good reason for sketching this graph? Well, so that we can actually find, the y piece. We should know what the y piece is because it's I, but what's in front of the I is a 1, so we're looking for the numerical value there. Okay? But when we graph this out, we can kind of see, right, negative 3 in the real direction and a plus 1i in the imaginary direction. So when we do that, you can take 1 squared plus square root of 3, negative square root of 3 squared, alright, all square rooted, and you'll get r is 2. Okay, once we know that r is 2, right, then we're going to go tangent inverse of 1 divided by the square root of negative 3. Okay, and that will give us the angle. the angle here is, we're doing it in radians for the example here, but it's 5 pi over 6. But in your calculator, you could do tangent inverse, okay, of 1 divided by negative square root of 3. You get the same thing, all right? You just have to subtract it from pi, and you would be good there. Okay. If we wanted to write it the other way, right? We know that it becomes what, R2 CIS 5 pi over 6. Cosine imaginary sign. So that's how we would write that out. Alright, let's pay attention to this one. We want to write negative 3i in trigonometric form. What's missing here is what the first thing, right? It doesn't look quite right. It's missing the real component. The real component is still a part of the problem though. It's 0 in this case. You need to make sure that you use 0. Alright, and the negative 3 is in the imaginary direction. Alright, so we can start by sketching the graph. So we go 0 in the real direction and negative 3 in the imaginary direction. So we're going to be pointing straight down. Okay, when we graph it, the blue is in the rectangular, so that's the negative 3 straight down. So 0 minus 3. Now, the other piece, okay, is going to be the location of it. So our angle there, we should know is what? 270. Well, how do we know that? Well, remember, the real part is the x part, the imaginary part is the y part. So we would be taking tangent inverse, okay, of what? Opposite over adjacent in this case. So we got to be careful, you know, when we do those sort of things. Okay, but let's go through the r first real quick. How do we get it? It's going to be 0 squared, so make sure that you incorporate that. Obviously, it's not going to impact the magnitude here. Okay, but 0 squared plus negative 3 squared is the square root of 9. Square root of 9 is 3. So that's the modulus. But this is where I was pausing before. I was getting ahead of myself one step here, but I just wanted you guys to know. Alright, you can't find tangent this way because it's what? Negative 3 divided by 0. We have division by 0. So you're going to have to find it a different way. Well, the only other way is for you to recognize that it's on the quadrantal because there's no real part. So when there's no real part, it's purely imaginary. It's either going to be positive y direction or negative y direction, or essentially the imaginary direction. Okay, so you should know since it's on that, it's going to be a quadrantal. Your choice is going to only be 90 or 270. 90 if the imaginary part is positive, and 270 if the imaginary part is negative. Alright, so when you graph that. So you have to recognize that it's a quadrantal here. Okay, and then we know that r is 3, so we write it in CIS form, so 3 CIS 270 degrees. Okay, so that took us to trig form, or polar form. Trig form, polar form mean the same exact thing. Okay, alright, so we want to write each, let's do another example here. We're going to write each complex number in its alternate form using a calculator approximation as necessary. Okay, so we have 6, which is our what? You should recognize that's our r. And then we have cosine of 125. The 125 is obviously the theta. So we want to find our two rectangular forms. So remember, x equals r cosine theta, y equals ri sine theta. So literally we can just substitute those in. So cosine of 125 is negative 0.57, and sine of 125 is 0.81. So then we take 6 times those, each one of those, and we get negative 3.44 plus 4.91 i. Always carry the i. The i is important because we're dealing with complex numbers, so don't just leave it off. Okay, so let's say we have this one. Okay, this is given to us in rectangular, so we need to be able to go the other way. So we can see that the x is 5, the y is negative 4 when we do this. So we sketch it out. Okay, we should end up in the 4th quadrant, and we should be taking 5 squared plus negative 4 squared. So you got 25 plus 16 Okay, that's 41, and then we square root that, we get square root of 41. So the modulus is the square root of 41, and you should be able to take tangent inverse of opposite over adjacent, so it's going to be tangent inverse of -4 divided by 5 to get the magnitude, and when you do that, you're going to get 321.34 degrees. Okay, but remember, you got to use the tangent inverse button on your calculator. So tangent inverse of -4 divided by 5, close the parentheses, okay? And we should know that we end up at 321 degrees. When you find that, though, remember your calculator is going to give you that -380 or 38.66. So what you need to do is remember, I got to take that away from 360 because I got to be in the fourth quadrant. How do you know you're in the fourth quadrant? Because it's based on your sketch. So remember, your calculator is always only going to give you a first quadrant potentially angle. If it shows up negative, you have to take that away from 360 or 2 pi. So when you do that, that's how you know to end up in 321.34 instead of using -38.66. Alright, so if we write it in CIS form, okay, square root of 41, CIS 321.34. Alright, last piece here we're just going to talk about a little bit is called the fractal, called the Julia set. Okay, so what we really want to do is to see if the complex number is in the Julia set. Alright, I guess first question is you're going, well, what's the Julia set? Well, in general, the most basic definition for it is the Julia set it's bound between points in a complex number plane. Okay, and sometimes we reference it as a Riemann sphere. We're going to get into Riemann sums and things like that in calculus soon. Okay, but it's really they diverge to infinity. Okay, and they remain finite under repeated iteration. Okay, so it's just doing some different mappings. Alright, the most famous one is the Mandelbrot set, and that's kind of what you're looking at right here. So that's really what the Julia set is, and we're just kind of seeing if these complex numbers are part of that set or not part of that set, and kind of how we go about doing it. Okay, so if we want to determine that the complex number is part of the Julia set, we have to do the following sequence, and this is sort of kind of a Riemann sum for us. Alright, but you got to go z squared minus 1 times z squared minus 1 squared minus 1. Okay, and then we have a whole pattern that we're going to continue. Alright, so really we just keep squaring and squaring and squaring and rewriting the set. Okay, so what we want to really do is, determine, okay, if the absolute values of any of the resulting complex numbers exceed 2, okay, if they're bigger than 2, the complex number z is not in the Julia set. Okay, so if you do that calculation and it exceeds 2, it's not in the Julia set, else it will be in the Julia set, and you would shade it in the graph. Okay, so example 5 here, we just want to determine whether each number belongs to the Julia set. So we're going to do a couple of them here. Let's start with A. It says z equals 0 plus 0i. Okay, so we want to determine if that's in the Julia set. So we start by following the equation on the previous slide. So we're going to say z equals 0 plus 0i equals 0. Then what we're going to do, we're going to do z squared minus 1 equals 0 squared minus 1 equals -1. Then we step into the next one. We have z squared minus 1 quantity squared minus 1. Okay, that equals -1 squared minus 1, which equals 0. So we're looking at that output right there. As it get outside of 2. Okay, and you can see literally we just keep substituting in. So if we look at this, we know the calculations are going to continue to repeat as 0, -1, 0, -1. So they're going to be repetitious based on just us doing the brief little calculations here for the Julia set. Okay, so if they're 0, 1, they do not exceed it. Okay, so the part is part of the graph, and it is in the Julia set. Okay, because the numbers did not get larger than 2 in this calculation. Alright, let's take a look at another example here. We have z equals 1 plus 1i. Alright, we're going to start just by substituting in. So we're gonna take z, alright, and we're going to square it, minus 1. So we're substituting in the z we have here. So we end up with 1 plus 1i, quantity squared, minus 1. Okay, that ends up giving us 1 plus 2i plus 1 squared. Be careful when you square that. Remember, it's not just 1 squared and the 1i squared. You have to FOIL that out, or box method. Remember, when you're squaring something, it has to be multiplied by itself. Okay, so when we get that first z squared, okay, we end up with negative 1 plus 2i. Okay, so if we take a look and find the absolute value, all right, we take the square root of each one of those. Okay, so negative 1 plus 2, or negative 1 squared plus 2 squared is the square root of 5. Okay, square root of 5 is greater than 2, so it's not going to be in the Julia set. You don't have to keep going on. You can just stop right there after you've done the check to see if it's in the Julia set or not. Alright, I try not to put too many Julia set problems on your homework. There might only be 1 or 2, but they're as simple as the 2 examples that we have going on here. So that's the end of 8.2, guys. If you have any questions, feel free to email me, or if you need a Zoom conference or a Teams conference, let me know. Else, those of you guys in class, go ahead and ask questions, and we'll go through some homework problems as well as you need them. Alright, guys, take care. We'll talk to you soon.